Hi guys, Mr. Thompson again. Welcome back. This is part two of the little guest teacher series on the Ready book in session 2 of lesson 5. This is going to be a two-parter. This first part we're going to go over pages 87 through 90, and then we're going to go over the practice pages in the video immediately following this one. Let's look at our learning targets for today. Of course, like yesterday and all through this week, we're identifying the constant of proportionality using word problems, and we're using the proportional relationship to solve multi-step ratio problems this week. So, let's get our brains warmed up. This time, get your piece of paper and divide it into 3 sections like this here, and label them A, B, and C. This is going to be a would you rather. So, on part A, would you rather? Would you rather earn $15 an hour for 3 hours of work? In part B, but would you rather earn $10 an hour for 5 hours of work? And in part C, write down earn $40 for completing a project. Flat fee. So which of these would you rather choose? Give it a second. Think about it. Write down some ideas. And I'll be back in a second, and we'll talk about it. So put me on pause and come back when you're done. Okay, welcome back. All right, so let's look at some of your possible solutions. Let's say that, well, obviously, A earns more money per hour than B does, but B shows the greatest amount of money earned, because you're working longer hours. Even though you're getting paid less per hour, you're earning more altogether. And C offers the best rate, but only if you work a certain number of hours, right? If it's a half an hour job, boom, take that one. But if it's not, if it's going to take you 6 or 8 hours to do, it's the worst. So can you compare option C to the other two? When is it the best hourly rate, and when does it get to be the worst? Well, it's the best hourly rate if the work takes 2 hours or less to complete. And it's the worst rate if it takes longer than 4 hours. So it depends on how long you work for that one. So, just a little something to think about, something that gets your brain working in a proportional manner. So, now let's move on to page 87. Now in 87 we are working on solving multi-step ratio problems. And here we have a sample problem to look at. As you can see, it is a walkathon question. Francisca and Elizabeth are participating in a walkathon fundraiser. Each girl walks for 3 hours. How much will they raise altogether? Now, in case you don't know what a walkathon is, that's where you go and pester your friends and family and neighbors and get them to pony up a certain amount of money if you walk a certain number of miles or a certain number of hours. And they pay either per hour, per kilometer, per mile, or whatnot. In this case, they're paying per hour. And the more people you get to shell out per hour, the more money you make for whatever charity you're walking for. So Francisca is earning $25.50 for every half an hour she walks. And Elizabeth is earning $14.50 for every quarter hour she walks. So if she's walking for 3 hours, how much are they going to raise all together? So put me on pause, work this out using whatever method you want to, and when you come back, we'll take a look at it. Okay, welcome back. What'd you come up with? I have a couple different ideas. That each of these circles represents 1 hour, and Francisca's circles are right here. That's Francisca. And that's Elizabeth. Now Francisca is earning $25.50 for every half an hour. So we can take Francisca's circles and divide them up into half-hour segments, while Elizabeth's are divided into quarters. So how many quarter hours and half-hour segments are there in those 3 hours? As you can see, we have 6 half-an-hour segments in 3 hours for Francisca, and 12 quarter-hour segments for Elizabeth. And how much are they earning per each of those segments of time? Well, Francisca is earning $25.50 per each of those 6 segments. And Elizabeth earns $14.50 for each of those 12 segments. So we can figure that out, right? We can multiply the number of hours times the number of segments. 0, 6, and 5 is 30. That's 30 again, which is 3, 18. So $153 for Francisca, and Elizabeth has 0, 5 and 2 is 10, 8 is 9, and 2, and then 14, 50, 0, that's 174, 0. Okay, so we got 153 for what Francisca has earned, and 174 for what Elizabeth has earned. So we can combine those two, right? Because we're looking for how much they're both earning together. So we can say it's 153 plus 174. And 153 plus 174 is, let's see, 4 and 3 is 7, 7, 5, 12, so 3. So 327. So they've earned $327 altogether. And that's one way to show it. It's not the only way, correct? There's other ways to do this too. So let's try another way. That's a visual method. Let's try the double number line method. So let's see what we have here. First of all, let's set up a number line for Francisca and a number line for Elizabeth. Now, both of them, you're comparing hours to dollars. There. So, we know that Francisca is earning $25.50 for each 1/2 hour that she runs or walks, and Elizabeth is earning $14.50 for every 1/4 hour that she walks. So we can figure out, if we know what it is per half an hour, we can figure out per 1 hour, and if we can figure out a 1/4 hour, we can figure out per 1 hour. So let's work on that. So let's say 1/2 to 1, you multiply by 2. So what's 25.5 times 2? Well, 25 times 2 is 50, and 1/2 times 2 is 1, so we have 51. And for Elizabeth, we have 1/4 times 4 is 1, so 1450 times 4 will get us to 58. So we have $58 per 1 hour for Elizabeth. So if we know how much it is per 1 hour, we can figure out how much it is per 3 hours. It's 51 times 3. Let's see, 3 times 1 is 3, 3 times 5 is 15. So it's 153. And 58 times 3, that is 174. So now we have 153 for Elizabeth. Oh, I'm sorry, 153 for Francisca, and 174 for Elizabeth. So all we have to do is add those two together, because we have 153 for one, 174 for the other, and combine those, we add them, and we get 4 and 3 is 7, 5, 12, and 3, 327 total miles there as well. So far there's two ways, right? Get the same answer both times. Now let's try it a third way. This time let's use our constant of proportionality and do it that way. So again, we have Francisca and we have Elizabeth. Now, Francisca had 25.50 per every 1/2 of an hour. And Elizabeth had 14.50 per every 1/4 of an hour. So let's take a look at that. So we know that 25.5 divided by 1/2 is the same as 25.5 over 1 times 2 over 1. And we know that, we'll do these both at the same time, we know that 14.5 over 1 divided by 1/4 is the same thing as multiplying by 4 over 1. So 25.5 times 2 is 51, and 14.5 times 4 is 58. So those are our two unit rates. $51 per 1 hour, $58 per 1 hour. So if that's what they're earning for 1 hour, let's figure out what they earn for 3 hours. So 51 times 3 hours and 58 times 3 hours gives you 153 for Francisca and 174 for Elizabeth. And just like before, that's what they both earn for 3 hours, so we combine those and we find that 327 is what we come up with. So 3 different ways. Each way we're coming up with the same answer. So our solution for this, how much will they raise together? They will raise $327 for 3 hours of walking. Oops. So you could have solved this any one of a number of ways, any one of which would have gotten you to the right answer. All right, let's walk through page 88 together. Now we're exploring different ways to solve these problems, right? We saw a couple different ways on the last page. So let's take a look. This is talking about the same question, Elizabeth and Francisca. Now, under the model it, we can identify the constant of proportionality from a verbal description, right? Because when we read that, she raises $25.50 every half an hour. Well, if she raises $25.50 every half an hour, that means she raises $51 every 1 hour, right? We could use equations this time, right? If we're using equations to model how much they raise per hour, notice we're defining our variables here. We're using M to represent dollars, and we're using H to represent the time. Okay? So we can find out how much they raise in 3 hours using that constant of proportionality. Because there's our constants right there, right? So if Francisca is raising $51 per 1 hour, then in order to make that an equal equation, you have to take that 51 and put that with the hours, right? So it's $51 per 1 hour. So you multiply the hours times 51 to get to your dollars. In this case, 51 times 3 hours. And 51 times 3 gets you to what you were looking for. In this case, 153. Same thing with Elizabeth. She's 58 times the number of hours, gives you how much money she's earning. In this case, 58 times 3, which is 174. So being able to build, as you can see, being able to build an equation from a constant of proportionality is a lot less work than working it out with double number lines and charts and stuff like that, like we were doing in the previous page. So let's take a look forward, and you'll see on page 89 we have 5 questions. So let's look at these one by one, and let's talk through them and see what you can do with them, all right? So, look at the first model it. That's the one we did before. How can you identify the constant of proportionality from a verbal description? So give me a pause, think about it, write it down, and then come back when you're done. Okay, welcome back. So, how can you identify the constant of proportionality from a verbal description? Well, here's one option. You can say that you can find the two quantities that have a proportional relationship, right? Find the 2 bits of data that you're looking for. Then you divide the first quantity by the second to find the unit rate. The constant of proportionality is the unit rate, as you well know. So think of that. Once you find your 2 bits of data, you pull those out, you divide the first quantity by the second quantity, that gets you the unit rate. Now, which way you divide those to find which unit rate depends on what you're looking for. So let's look at the second model it. Where is the constant of proportionality in each equation? And how can you use it to find how much money each grower raises in 3 hours? Okay, now remember the second model is where we made those equations based on money equals the constant times time. So, looking at that, how can you use it to find how much money each grower raises in 3 hours? I wouldn't even pause for this one because it's pretty obvious, right? In both equations, we'll go ahead and put that down here. In both equations, the constant of proportionality is just the coefficient of h, right? The constant of proportionality is the coefficient of h. And then you just substitute. Substitute 3 for h to find how much money each raises in 3 hours. So in that equation, the coefficient of h is the constant. The constant, as in the constant of proportionality. Aha! So how much money do Francisca and Elizabeth raise together is question 3. Also asking, you could use the equation M equals 51 plus 58 each to find the amount of money they raised together. Ooh, how does that work? Now all of a sudden we're looking at a more complicated equation here. 51 plus 58 times H equals the amount of money they raised. Why does that work? So put me on pause, think about this, work it out, and when you're done, come back, we'll talk about it. Okay, welcome back. Yeah, let's take a look at how this works. So if the equation is M equals 51 plus 58H, that means those are the two constants of proportionality added together, right? This is Francesca's and that's Elizabeth's. So we can add those two together, and instead of adding the totals after the equation, we can make it all together into one equation. So what is 51 plus 58? That is 109. So let's write that down. Let's say M equals 109 times H. That's how much money they're both earning together per hour. So if we multiply that by the number of hours they've both walked, 109 times 3, that should get us to the amount of money they both earn together, right? So let's try that. What's 109 times 3? Well, 3 times 9 is 27, and 3 times 1 is 3, so 327. Hey, that works out. So $327 is what they've all earned together. And that's how that works. Why does it work out so easily? Well, because you're finding the money each girl raises per hour. Add those amounts to find the total for both girls. Per hour. Then multiply by the number of hours both walked. Boom! Easy as that. Okay, we won't put the boom in there. So, move on to question 4. So you've identified constants of proportionality so far in tables, in verbal descriptions, in graphs, and in equations. So why is this helpful when you're solving problems that involve proportional relationships? So I'll give you a few seconds to answer that on your own. And then we'll come back and I'll talk about why I think it is. Okay, welcome back. So why is it helpful? Well, because being able to identify, I can't talk and type at the same time, the constant of proportionality in many ways lets you use the form that's most helpful for you to solve the problem. So think about that. You don't have to go through, like we did on that very first page, those long involved processes to try to, graphically figure out what it is. If you can just determine what the constant of proportionality is, you can write an equation from that, solve it. In many ways, that's the simplest way to do it. So here's a reflection. Think about all the models and the strategies that we've discussed today, and describe how one of them helped you better understand how to solve that try-it problem, the one we did at the very beginning. So there's a lot of different ways to do it, right? We used visual representation, we used a double number line, we used equations, we used the constant of proportionality, we tried division, all sorts of different ways. So what way helped you the most? And I'll let you work on that. Of course, there's nothing I can do to answer that because it's different for everyone. So whatever it is for you, you answer that question for yourself. Let's move on up to page 90 and let's look at some of these apply it questions. And I'll talk you through how you solve them, and then you can try it on your own and see how you do. So let's look at question 6. At a certain bookstore, doesn't say what it is, Books A Million? I don't know, could be anything. At a certain bookstore, you get a $5 coupon for every 4 books you buy. What is the least number of books you could buy to get $15 in coupons? And show your work. Okay, let's pull out some data first, and then I'll let you work on it, and then we'll see what we did, all right? So, what's our data? Well, we got a $5 coupon for every $4 worth of books. So it's a coupon for every 4 books. Now, you know that keyword "for" there means that you're looking at $5 per 4 books. So that's a hint of setting up the ratio, perhaps. What is the least number of books you could buy to get $15 in coupons? So you're looking for your answer in the terms of books to get coupons, right? So we're looking for the number of books. So our answer is going to be in terms of books. So give that a shot. What do you think? Work it out. And when we come back, we'll talk about it. Okay, welcome back. All right, let's take a look, see what we have here. First of all, we know that we are looking at $5 per 4 books. So you could have written this down as your data. And we're looking for the number of books per $15. So you'll notice the way this was set up at first was a coupon per every 4 books. But what we're looking for is the number of books per $15. So the way you set that up will determine how you find your answer. I'm going to go with, we're looking at books per coupons. So I'm going to do it that way. I'm going to say, all right, we want 4 books per $5 in coupons, because we're setting up our ratio so that it looks like this, right? Books per dollars. So if we have books per coupons, that's like saying 4 books per $5 in coupons. So 4 books out of $5 in coupons is a ratio of 4 to 5. And so you know by dividing that that is our unit rate. 4/5 is the unit rate. So now we can set up an equation using 4/5 as the unit rate. So let's see how that looks. Now we're looking for how many books to get $15 in coupons. And we know it's 4/5 of a book per dollar of coupons. Because that's what our unit rate is telling us, right? It's 4/5 of a book per 1 in coupons. So 4/5 of a book per $1. So let's set that up over here. We'll say that we have books and we have coupons. Now we know that since it's 4/5 of a book per coupon, then we need to put our 4/5 as our unit rate on our coupon side, right? Because if it's 4/5 of a book per coupon, we need to multiply the coupons by 4/5 to make the number of books and the number of coupons in this equation equal. So books is 4/5 the number of coupons. It looks like that. So how many coupons are we dealing with? We're dealing with $15 in coupons, right? So if we have $15 in coupons, that means the number of books is 4/5 times $15. So books equals 4/5 times 15. Go 15 over 1 because we're dealing with fractions. And hey, we can cross simplify here. We can say 5 and 15. 5 goes into 5 once, 5 goes into 15 3 times, which means that's 12 over 1. And if that's 12 over 1, that means the number of books is 12. And that's got to be the answer to your question. How many books can she buy to get $15 in coupons? 12 books. So if we were to write the solution down, we can write that she would need to buy 12 or more, because it said what's the least amount she could buy, right? So she didn't have to buy 12. She could buy more than 12. Be sure that you have that in the answer, because the question actually was specific about that. She would need to buy 12 or more books to get 15 buckaroonies in coupons. So that is the way I have that question set up and answered. Let's look at number 7 now. Number 7, swim team members can race or dive. At a meet, 18 of the members race. The ratio of racers to divers is 6-2. How many members are on the team? Well, this throws you for a loop, doesn't it? This isn't what you were expecting the question to ask. And show your work. So let's figure it out. Let's pull our data, all right? Now, we know that we have 18 members that are racing. Now, we also have a ratio. A ratio of racers to divers is 16-2. And what it's asking is, how many members are on the team? So definitely a multi-step problem here. So figure it out, put me on pause, see what you can do, and we'll come back and take a look at it. Okay, welcome back. So, because we have a ratio of 6-2 racers to divers, we can write that as a proportion, as a fraction, right? We can say that we have racers to divers. And that ratio is 6 racers for every 2 divers, right? So we have to get from 6 racers to 2 divers. Now we know that we have 18 members racing. So if we have 18 members racing, we need to find out how many divers there are. And we can use the proportion for that. So we can say, if there are 6 racers to 2 divers, if there are 18 racers, how many divers, D, how many divers would there be? So if 6 over 2 equals 18 over D, how would you solve that? Well, let's solve it like an equation. Because we can do that, right? Because we're familiar with these. We did one-step equations last year. Well, we can take 6 over 2. For one thing, we can simplify that, right? We don't need to work with 16 over 2. We can reduce that down to 3. Because right now we're just solving an equation. So 6 over 2 equals 3. 3 equals 18 divided by D. So we got to get the D from the denominator up to the numerator, right? And you know how to do that. You have to multiply both sides by D. So if we multiply 3 times D, that's the same as multiplying 18 times D divided by D.
right? All we've done is we've multiplied both sides by d. We can do that. And if you do that, you will notice that these two d's cancel out, don't they? Because d over d is 1, and 18 times 1 is 18. So that gets rid of those d's. That gives us 3d equals 18. So I'll go ahead and pull this up here. So if 3d is 18, aha, we know how to solve for d. All we have to do is get the d by itself on one side of the equation. So how do we do that? We divide both sides by 3, right? We divide 3d by 3. We divide 18 by 3. Both of those 3's cancel out. This looking familiar from last year? I know it's been a while since we've done equations like this, but that's all right. That gives you d equals 18 divided by 3. 18 divided by 3 is what? 18 divided by 3 is 6. So d equals 6. Now, is that the answer to our question? No, it's not. Because that just tells us how many divers we have. Remember what the question was asking. How many members altogether are on the team? Because we knew we had 18 racers. We knew that from the beginning. So we need to find the number of divers to add those together to find the total amount. So we have 18 racers. So we can do 18 racers plus 6 divers. So 18 racers plus 6 divers gives you, what's 18 plus 6? It's 24. So 24 total people on the swim team. And that would be your answer. Now, if doing the equations freaks you out, that's okay. Here's another way to do it, right? You can just use it just like you're solving with proportional fractions. You can say if, I'll write this down over here, you'll say if there's 6 over 2 equals 18 over something, well, what do you have to do to 6 to get to 18? You have to multiply by 3, right? 6 times 3 is 18. So you do the same thing on the bottom. 2 times 3 is what? It's 6. So that means d equals 6. So we have 18 racers and 6 divers. Got to add those two together. And 18 plus 6 is 24. So that's another way you could have done it if you didn't want to get all algebraic. So the solution, how many members are in the team? There are 24 total members on the swim team. So if your answer looked something like that, very good. Let's look at number 8 now. Roberto runs 25 miles. His average speed is 74 miles per hour. He takes a break after 13.9 miles. How many more hours does he run? And show your work. Well, that's an interesting question, isn't it? So now we're looking at miles per hour. Okay, well, we know that miles per hour is a ratio, so we can pull that data out right away. So we're going to be working with 7.4 miles an hour because we're looking for how many hours he's running. How many more hours does he run? So our answer is going to be in terms of hours. So we're looking for hours. The rest of our data is the miles. He's run 25 miles. He takes a break after 13.9. So how many more hours does he run? Not how many miles does he run, how many hours does he run? That should be a hint. So put me on pause, work it out. When you get done with it, we'll come back and give it a discussion. Okay, welcome back. So how'd you do? Let's take a look at this one. Let's see what we have. Well, first of all, we know we know that our constant of proportionality is 7.4. Because of 7.4 miles per hour, that's miles per 1 hour, that's the unit rate, and since it's a constant rate, it's a constant of proportionality. So let's write that down. We know that 7.4 is our constant of proportionality. Now, we're looking for how many hours he's running. So we also need to know how much farther he needs to go. So we can't figure out how many hours he needs to run until we figure out how much farther he needs to go. So that's what we need to do first. So he's run 25 miles, and he takes a break after 13.9. So we can say he's run 25 miles total. And so far, he's run 13.9. So that tells us that we have 11.1 miles to go. So we have 11.1 miles to go. Now we can figure out, we have a distance, we have 11.1 miles. We have a speed, 7.4 miles per hour. Now we can figure out how many more hours because we have all the data that we can put into our equation, right? So we have miles per hour. Now that's easy to figure out, right? Because that's our constant of proportionality. So if we have 7.4 miles per hour, that means we're setting up miles and hours. I have it 7.4 miles per 1 hour. That means your 7.4 in your equation goes over here with hours. 7.4 times the number of hours gives you the number of miles. Now we just need to plug in our numbers, and we know that how many miles has he gone? He's gone 11.1. So 11.1 equals 7.4 times the number of hours, right? So we know how to solve this equation. We need to get the variable h by itself on one side. So to do that, we got to take that 7.4 and move it over to the other side. So how do we move 7.4 times h over here? We have to divide by 7.4, right? Ah, it's all coming back to me now, isn't it? Yeah. So 7.4h divided by 7.4 and 11.1 divided by 7.4. Because whatever you do to one side, you got to do to the other side. Now 7.4 over 7.4 is 1, so that cancels out. So what we have left is 11.1 divided by 7.4 equals h. 1 divided by 7.4 will tell you the number of hours. So do you want to keep it 11.1 divided by 7.4? No, let's make it an actual number. Let's see how many miles he really has to go, or how many hours he really has to go. So let's work that out. What is 11.1 divided by 7.4? Well, let's work out some good old-fashioned long division. We have 7.4 and we have 11.1. We're dividing. Now we know we can move those decimals over one place. So 74 divided into 111. So how many times does 74 go into 111? Well, 7 times 2 is 14, so it wouldn't go 2. So I'm guessing it'll go once. 74 times 1 is 74. And 111 minus 74 is 37. And bring down your 0. So how many times does 74 go into 370? Well, let's do some estimation. We know that 7 goes into 37 5 times, because 7 times 5 is 35. So let's try 5 and see if that works. Let's try 74 times 5. That gets you 27 times 30, and 37. Aha! Look at that, 74 times 5 is 370. So we'll put 5 down there. 370, no remainder. So we figured out now that H, how many hours will he be out? He will be out for 1.5 hours. So our solution to this, how many hours does he run? He runs 1.5 more hours. So that's what that problem looks like. So that will take us to the end of the first section of session 2. And when we come back for the next video, we'll pick up with page 91 and we'll work on those green pages. So, till next time, see you later. Bye.